Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, welcome everyone. Welcome to the last session of the day. Hopefully it will be the most interesting one. All right, so we thought that we'll just sort of initiate the discussion by asking some concrete questions to the panelists, and then we can just have a discussion going, and everybody is welcome to chime in. So the first question that we were thinking was, like it's to everyone here, that what do you think are sort of the big challenges in machine learning? What do you think, like if you, let's say, if you think that, okay, this is one area that I can solve, or this is one problem that I can solve, then this will really make a big change to the world or to the science. So maybe I'll start with Chisan. Okay.
Oh, okay. So now we have a big question is about what are the most challenging things in machine learning. Okay. So in my opinion, I think machine learning. So right now, machine learning is a hard topic, and so hard to the point that sometimes people think that maybe the bubble is there is a bubble forming. So the problem is that machine learning is often part of a whole application. So right now, in many applications, that machine learning is used, but it's only one component of the whole thing. And sometimes it's very difficult to know if that, like improving the machine learning part, actually give you something for the whole application. So that's actually a big issue. Then another thing is that in applying machine learning in those application areas, then usually there are so many things you need to decide. And the machine learning is not an automatic process yet, so we don't have anything called automatic machine learning. Well, even though right now quite a few people think that's an important research area, but those are very challenging issues. It's just not that easy to make a machine learning fully automatic. Therefore, many our users, they have big problems to use machine learning. So roughly those are what I think right now the maybe most challenging things in the coming future.
Yeah, I think I agree with what Chijan said. It's, of course, many people out there, whenever you talk with them, they think it's a magic word solves everything, but it's very far from being fully automated. So one of the things I think is, there are several things related to what Chijan said that I'm interested in, and I think these are also upcoming challenges and current challenges. One is how to represent data, and data representation is either a part of machine learning, but it's also pre-processing because it is related to realities of how to collect this data, the cost of collecting data, noise in data. There are many things. So getting data in a shape that you can do learning with it is, for any realistic data science type problem, one of the hardest things, and that's where vast amount of user effort still goes, and how to reduce that, how to automate that as far as possible while still being able to get out the inference from it that we want, that will remain kind of sketchy for a long time, which is then also I think in my opinion quite closely connected with a different aspect, is to the aspect of, can we somehow, based on a more high level description of the task, automate the construction of a rich enough family of mathematical models which can help us go from the data to the prediction that we wish. And fully automating this is it's currently a near-term challenge, but as our understanding and as these things grow in complexity, it will, for many years, I think, remain a challenge. So those are just echoing what Chijan said, but in slightly maybe different perspective.
I think, can you hear me for this? Okay, good. So I also agree with what the previous two people said. I think what I could maybe add to the challenge of the different types of machine learning that are there that's maybe also difficult for the user is that often machine learning is applied in application, but people might not really understand what are the assumptions behind the model. So I think communicating what are the assumptions, what you can do with the model and what not, and how much you can trust the model and how much you can maybe not trust the model, maybe where you can, even that the model tells you I am certain or I am not certain, might be an important thing in the future if you actually want to base some decisions on what the machine learning model does, if you want to actually use it. Another thing that maybe ties to what the other two said is that, well, one is representing data, one is sort of representing models and basically designing models that capture what the application actually wants and not just using something off the shelf. So really understanding what's the application about and capturing this in an appropriate way. So basically what are mathematical structures and what's an appropriate representation that we can, but that's also computationally feasible. And from the analysis perspective, it's maybe also making assumptions that are realistic in the analysis, maybe realistic assumptions on the noise and the actual data that we have, understanding that better. Yeah. Other things that people are working on is, of course, things like scalability of the algorithms, that kind of thing.
Yeah, so adding and building upon what Stephanie has just introduced, the whole concept of structure, right? So, so machine learning, I think, is rather unique in the sense that it is one of the sort of fairly interdisciplinary areas that has come about as a confluence of several other very classical areas, right? So you have optimization, you have as varied fields as natural language processing, statistics, computer science, and so on, right? So it's something that cares both about notions of information and measurement, as well as notions of recovery or computational capabilities. So in that sense, it's really I think set out to try and solve big problems involving lots of data, maybe in an imperfect, largely imperfect or corrupted fashion that one works with. So in that sense, I think sort of conceptually, what appears to be the case is the search for identifying and exploiting as much structure as possible in different types of problems that various disciplines might pose in the sense of machine learning. So I think one big sort of conceptual challenge is to try and either in an automated way or in other ways try and identify structure that will help you to really push the limits of machine learning procedures. I mean, whether it be trying to show develop some non-convex methods that previously were thought to be sort of impractical, but that work really well in the presence of some specific structure, or large scale sort of inference problems, whatever that, or even large scale optimization problems with specific structure that now become tenable once you identify some specific structure that you can exploit. So I think that is my perspective on what one of the directions that learning algorithms are going towards.
Good. So I have some questions about some of the things that speakers have said, but before that, does anyone in the audience have any question or any comment? I think so. Yeah.
Sorry, 1 minute, just to interrupt you. Can you just briefly introduce yourself before?
Yeah.
It'll be good for everyone to know sort of who everyone is.
Myself is Amrendra Mukherjee, a PhD research scholar from ISU.
Okay, sorry.
So Yes, sir. So the question is, like, so which one? Which one is kind of more important? Computational or the fundamental statistical issues which are still there, like trend distributions, finding probabilities.
I'll make some comments on that. So machine learning, to me, is fundamentally like any other realistic discipline, a discipline of trade-offs. And one cannot give a generic answer of which way you should be trading off things. So for example, I talked a lot about convex optimization, but convexity is convenient, and not everything may be naturally formulated as convex problems. So now, should we chase the theorem and just forcefully look at things through a convex lens or not? And so it's what kinds of trade-offs are we willing to make? Or, so the best example of this is, one of the reasons why these simpler optimization techniques are so popular in machine learning, people say that, well, we have large amounts of noisy data. I'm okay optimizing my models to an inferior level of accuracy than a numerical analyst who writes an eigensolver would care about. And we made that trade-off that we accept these low accuracy solutions, but what huge benefit we get from that. We can crunch through lots more data, because our ultimate aim is not to really fit the tiny epsilons of the model, because the model is always wrong, but to try to be able to process more data in the hope that we can do better generalization at prediction. So that motivation is coming statistically, and it is matching quite nicely with the mathematical computational framework. And machine learning actually is unique in the sense that it cares about both. And in some nice lucky circumstances, you can even mathematically characterize how those things trade off. In some you cannot. But every time you design a model, you should always ask exactly the kind of question you asked, and there will always be a trade-off. And whether that's a good trade-off to make or not, you should never really decide a priori. Just try it out. See it on actual data, on actual problems. So start with the data is really the statement here. And then use your understanding and empirical, extremely important empirical experience to help make a good trade-off and decision. Anybody else?
So here I'll actually, it's more of a question. So for the last question you said that we want to automate machine learning, whereas here you are posing an entirely different approach. You are saying that an expert should sit and he should look at the data and then figure out what model to use and everything. So there seems to be a very and that sort of thing happens quite often. Like we either say, yeah, we want everything to be automated, or we want that an expert should sit. So do you have a sense of how one should try to think about it? Like one should should he just try to aim very high, automate everything, or when he's let's say working on a problem, should he just look at the problem and go very deep in it? Pick an application, let's say I'll pick an application in vision, go very deep in it, and then figure out all my algorithms. So from research point of view, what do you think is the better option or correct approach?
Well, I think from pragmatic point, at least for the next many years, you cannot get rid of the expert hand. But if you can understand the trade-offs that are at play, and you repeatedly see these trade-offs happening across more than one application, then these things start becoming slightly automatable. But without exploring that, I think it's hard to make a sense of what could be really automated.
Okay. So my question is even a little bit more sort of low level, in the sense that I'm saying that, let's say many of us are here, researchers or PhD students, and also whenever there is a problem, should we abstract the problem out and just look at very abstract problem, or should we dive into an application, like pick up an application and then try to solve that application very well?
Well, I guess I'll let also somebody else speak, but
yeah.
I'll just quickly answer. Well,
like a chicken and egg problem. You need to solve a specific problem as well as try to look at the generically similar types of problems and solve it algorithmically.
Yeah.
But also look at specific problems if you would like to solve specific problem. And what I feel is machine learning is still in the necessary state where it is still model dependent. And model or fitness function or something, these have to be, I think, selected properly, and the model has to be selected properly, only then the thing can work. So I don't think it can be automated in that sense.
But if you look at the deep learning thing, it's like getting transferred to all the domains, like from NLP to image processing, computer vision, and all the other things. So that is
deep learning is one way of automation of that.
Yeah. So like, which is a better approach, like going for deep learning and which we don't know what the features have been learned, or should we go and manually engineer the features and then get a model?
Here I have one comment, which is that have you tried to run a deep learning system?
Yeah, it fails in many objects.
So the thing is, there sure the system is very generic, but all the complexity has been transferred to training of the system, and you need a lot of expertise there. So, and the way you will set your parameters might actually dependent on your application or your domain. So again, I don't think one can say that deep learning is completely independent of domain and you can just take your neural networks, apply it, and you will immediately get very good results. Like if that was the case, then I don't think everybody would be caring so much for Jeff Hinton and Jan LeCun and all, right? So, so still, I mean, expert advice is very important there also, despite the promise that it will lead to automation of features.
So also, one more, sorry, you were so I was just about to answer the previous thing that Prateek had mentioned. I think when I have a real data problem, to ask even the right question what I should do with the data, I would rather first spend a lot of time closer to the data before trying to throw any models or anything else at it. Because it could be that many of the things I may try in the beginning, they may give me some insight, I may try them, but they may be superfluous. So it's like the way physics connects to math. You have to pay the price of experimental observation before you begin to abstract out and create a grand theory that starts explaining. And then you verify the theory. But it's like you said, it's also chicken and egg. But still, I think for any new data problem, if this is the first data problem you're looking at, then certainly you should look at the data as closely as possible to be able to ask the correct questions. So this has happened to me in a few applications. Just to be able to even pose which question I should be answering, it's really important to go close to the data. And coming back to what Prateek said, I also agree. Neural networks or deep learning business right now, I may view it as we are using a computer to extend the human intelligence, because the expert knowledge is going into making the architectures, controlling other parameters, etc. before this thing works. And there are million other data domains where you cannot even, without significant more application of the human mind, you cannot even start to maybe do these things. Not necessarily for mathematical reasons, but for other reasons which we may forget, but these are practical reasons from real life. They may be legal reasons, privacy reasons, that you just cannot access the data in a way that your deep system requires access. Those practical issues will only be more serious. So it is important to, that's why representation or just seeing how you're consuming the data, I think, is very important. So you were
Okay, so let me say a bit about the, okay, well, I think the original issue is to ask about if you have a problem, should you like get into the details of that application or try to think like a more general abstract way of thinking. Well, I think in the area of machine learning, usually what happens is that in the beginning, for a certain type of applications, that people don't know what type of methods are the most suitable, then it's like a crowdsourcing kind of things, that different groups, they try different methods, but things then will converge. That's usually what happens, at least from my observation. So for example, like you can see why like in why deep learning things start from the image domain. Yeah. So it's like a lot of people, they somehow try this thing and find out that it works. Then a lot of people try to reproduce the result. Or so, say, for example, in computational advertising, in the beginning, people didn't know how to train a model to do click prediction. But now almost everybody use like to run very large-scale distributed logistic regression. That's after some kind of some type of experiments by different people. But once after that, the next thing is that now you need to figure out why these kind of things work. So for example, for deep learning, now a big problem is, because now deep learning is right now like a black box. Okay, so now you just put like multi-layer something, and suddenly it works. But can you provide a certain theory to explain why these deep learning systems are much better than some other existing things? Those things are very important and challenging things. So usually I think for a whole topic is that you need to try some kind of more engineering work to make things work. But after that, you need to study the theory. I think that's the way to do it.
Yeah, I would have also said that to really get an application work usually requires much more than just taking a model off the shelf and applying it, but really doing engineering and studying what works and so on. And it's a lot more work to make something really work in practice. On the other hand, what you will also find then is, based on your empirical observations, that sometimes there are interesting theoretical questions popping out. Like, for example, deep learning, why does it actually work? And you might also observe for other things, I've had this in my research too, that you apply a model even though in theory, in the worst case, it shouldn't work, but you see it actually works well in practice, so then you can start asking, so why does it actually work? And does this generalize to other things? Now you've really understood what are the properties of this model and approach. Does this generalize to other settings? Does it generalize to other applications or so? So these things are not really an XOR. It really goes together in some way.
When we talk about machine learning or optimization, then we are reducing some data, such like Pratik sir, reducing the number of vectors, and so means we are somewhere compromising with the accuracy. If we can analyze large data, we will get more accurate results than compared to the smaller data. Okay. But there are some frameworks like MapReduce based approach and platforms like Hadoop, and they can use clusters and can analyze very, very big data sets in very few seconds and milliseconds. So why we use machine learning for optimization? Why can't we use them? If we can get results on a large data set, then they will be more accurate than this one. If there are many assumptions, so maybe there will be some compromise with accuracy.
Okay, so I'll start on this.
So I think even if you use MapReduce or so, you will still need an algorithm that is actually running on that system. So you will need some algorithm that actually does the data analysis in the end. MapReduce is just a computational framework, and that algorithm will be a machine learning algorithm. And now you can, of course, there's a different question about, like, the more data I have, maybe the fewer assumptions I might need to make. In some cases, more versus less regularization or so. But you will always need like an algorithmic framework, like a model that you're actually learning. It's the analysis requires some.
Mainly optimization algorithms are iterative, means they are one step is dependent on another one. So, but when we work with MapReduce based approach, there are simple algorithms which can be easily parallel. We can make them parallel. So
I think that's a misconception. So let's say even if you want to do an eigenvector computation on a MapReduce framework, it's very hard. In fact, it's a big research problem how to speed it up over a single box computation. Like if you have a single box with 8 cores, that turns out to be much, much faster than if you do this computation over MapReduce with even 200 machines. So first of all, it's not that you can just throw like lots of clusters at a problem and the problem will be solved. In fact, a classical example of this comes from the domain of deep learning. So like if you remember a few years back, there was this amazing work by Andrew Ng and his team, which used around 1600 clusters to train a deep network after around, I think, 7 days or 10 days worth of using this cluster. And then later on, using proper algorithms and proper techniques. Well, not that they were not earlier, like Andrew was not using proper techniques, but by using very specialized techniques and specialized algorithms, Jeff Hinton's group was able to achieve similar numbers after just training for 7 days on a GPU, which had, I think, 8 cores or something like that. So you can see, like, huge difference. Like rather than using 1600 machines with multiple cores, here he is using one GPU, but using it in a proper manner so that you can, optimize much faster. So MapReduce, number one, is not the answer to everything. Another thing is that if you have a lot of data, that doesn't mean that the problem is solved immediately. Sure, as Stephanie said, that many of your assumptions can be realized. You might not need to regularize a lot, but still you need to apply proper algorithms that will use those data points properly. And again, many times you have budget issues. Like you cannot just say that, oh, I have a lot of training data and I'll just let my algorithm train forever. You might need your, let's say, algorithm, let's say your ranker to be trained within 5 hours. So in that case, you might have to do a sort of choice that do I get a very accurate solution or I get a solution within 5 hours. So again, there, many of the techniques that Suvrit and Chizen talked about, like stochastic gradient descent, or doing some very cheap techniques which optimization people will laugh at, but still they might give you reasonable solutions. So you might, like, depending on your system, you might need to design your algorithms properly that will optimally use your system.
There's a related comment actually to that. In fact, because iterative algorithms in general are not friends of MapReduce, that led many people to invest a lot of research effort in creating systems frameworks to better support iterative algorithms. So by now, each company reinvented its own. Facebook has its own, Microsoft has its own, Google has its own, other companies have their own. Different research groups have invested a lot of effort in creating frameworks which are better suited for iterative computation with persistent state and whatnot. So it actually, the demands of machine learning applications triggered a huge amount of research in systems, networks, architecture, OS, etc. So it's actually, so they work together quite nicely. And related to what Pratik mentioned, some of the algorithms may be simple, but a lot of the actual victory of these methods in large-scale industrial applications comes from significant amount of high quality engineering effort being put into making these things run with time budget, resource budget, failing hardware, and all sorts of things. So it's still a very active area, and ultimately, if I'm running my computation on the cloud as a user or even as a company, I have a limited budget, not only of time. Each extra hour on 1600 or 2000 cores costs a lot of money. So you want to, that's why know your model better, to come up with better algorithms, to also reduce the running time there and benefit not only that you get higher quality predictions, but everything happens with much smaller budget of both time and money.
Hi everyone, I am Sunil, research scholar from IIIT and even work for Infosys. So Infosys Labs, we are doing this machine learning application. So this is an interesting topic, how much we can automate in the machine learning, because I am seeing in past couple of years, how can we apply different models. It can be as simple as the clustering or classification models, but I am getting models, data from different domains. I am talking about the practical data. So we are well versed with the basic algorithms, whether it's a classification or clustering. But it is taking a hell amount of time to read the data and what model will fit it for them. So it may be a simple example where okay, it may be a ticketing description, for example, where I am using NLP techniques to convert it into the model and give it to a classification model. I am trying to predict the model in the sense, okay, if the new ticket comes, so what will be my solution? That it be, I want to automate that part. So I have a lot of historical data and we have a lot of models. We are using even the big data analytics, whatever the tools we are talking about on Spark MLA, Barar. We don't have any limitation on that front. But each case is very unique there. In the same, if I work for one set of data, I'm not pretty sure if the new set of data comes, can I use the same model? So how can we tackle these kind of issues? Because once we tackle this, then I think we will be approaching towards automating that process. We have different models, but I'm not sure what kind of model will suit for each data. That's where most of our effort is going. So how can we improve that kind of process, or structuring the model? And then we are doing a lot of pre-processing, as you mentioned, a lot of time spending with the data. Then I may be trying with all possible top 5 models which will fit. Then I'm validating which will fit for this one, I'm giving it. Maybe that is just like a customized solution for one. But can we improve that process? I think that will trigger to the basic theme what we are talking on, how much we can automate.
So automatic machine learning has like there are many things related. Because if you want to fully make machine learning automatic, that's very complicated. So about what you are thinking is like okay, how to like easily try different experiments on data, and once you have data, how to like to manipulate them or use them in the future. Well, there are certain directions going on right now. So for example, now there are research trying to connect machine learning and the user interface. So for example, traditionally you see like you see how machine learning or data mining software look like. They are not that interactive, or their user interface is not designed in a way so that you can easily like adjust the way you train your model. Okay. So some HCI people are involved right now in trying to improve these kind of things. Then there are also some efforts. It's like now if you have several models and you want to try all of them. So behind that, so one direction is if you store those models on the cloud. So and once you have a good mechanism, then you can easily do a kind of so to sweep all the models to tell you which one is better, because those models are independent. So it's possible if you have enough computing power. So those things are possible. And then to further give you like another similar direction is a lot of some companies, they are doing the so-called web-based machine learning. So those are like a bit like the next generation of machine learning package. Because traditionally you download R or Weka, these kind of packages. But in the future, because your data may be already on the cloud, and also traditionally for Weka and those things, sometimes you still need the command line mode. But a lot of people they don't write programs. So what if you can use mouse just to click on, say, okay, I want to do data split, I want to do classification. Yeah, so some efforts on that. Actually, I think Microsoft Azure ML is actually one example. I think next week in the workshop they even have a training session on. That's a bunch of companies are doing such things. So those are the small efforts to try to address your issues. I think your question. Yeah.
I'm Ankita. I'm a PhD student at IIIT Delhi. So I have a question regarding, let's say if I want to enhance the performance of an existing system, so sometimes it's like you add more data and build a model over it, or you build a better model over that existing thing instead of adding more data to it. So what is more important? Is it the data or the better modeling? Sometimes even by adding different kind of data, you can enhance the system, the performance of the existing system, and sometimes it's mostly by addition of more data you get better results rather than by doing better modeling over the existing data.
Yeah, I think, in general, definitely, like whenever you start a problem, you should try to get as much data as possible. Like whatever side information you can get, you should definitely get in the system, and then apply good algorithms which will automatically let things, which will automatically figure things out. So in fact, so a lot of things that I talked about the sparse linear regression. So one big motivation for that is coming from that direction only. That is, in companies, what happens is, we have this, amazingly bright software engineers who are very enthusiastic, who have their own features, or who have their own ideas that if I add this extra information in the system, it should improve the system. But many times the result don't match, and the reason is because learning algorithm then started to overfit or was not handling the data properly. So you want to design algorithms which can handle a lot of data without overfitting or without running into these type of issues. So the goal should be put as much as data as possible in the system, but design algorithms which will be able to handle that data, which will not overfit to the data, or which will not get confused by the data.
For a particular application, you have like some set of features, but now with the addition of more data, you have another set of features. So is it the...
So you should just concatenate the features.
No. So sometimes with the existing features, you build another model. With that, you can enhance the performance of the system. And there is another way by which addition of new features, you can enhance the performance of the system.
Yes, so that's why I'm saying that, if I understood the question correctly, that you should add more features to the system, and the goal should be that performance of your algorithm should not decrease by adding more features. That you have to ensure, that the algorithm does not suffer by addition of more data or more features. But certainly, like if you add data, you should expect more and more performance.
Unless the features are contradictory.
Yeah, so that's why your algorithm should make sure that it is doing correct feature selection.
So it could be that sometimes you may need to slightly grow the model with a richer class of added features, but if you don't have additional knowledge of how the new features relate to the existing features, then it's slightly harder to fully exploit it. But otherwise, like as Prateek said, if you're adding additional side information which is correlated in the same way with the prediction as the previous features, then you should be able to benefit from that.
I am a student from IIT Madras, undergrad student from IIT Madras. My name is Parth Thakur. Yeah, I wanted to ask, well, in communication field, the focus from wired communication to wireless communication shifted a lot, majorly because of the technological developments. Now, does a similar analogy hold in machine learning and all these fields as well? As in, what are the major front runners in the technology aspect of the same? Then what do you see, which research, as in some major front runners which are focused on the research or something of that?
Okay.
I can also say something to that. But I guess if you think of it, this also happens and will keep happening in machine learning. For example, neural networks have been around for more than 30 years. Now, because we have more computational power and we have more data and we can crunch that, and with the other bells and whistles that are there, but it's actually thanks to this gigantically increased computational power that suddenly these things are showing results that they couldn't back in the day. And so in machine learning, technology is not necessarily just the hardware, it is data is the major currency of machine learning. And if you have more data and you can crunch through it successfully, that is what transforms the capability of many machine learning methods on problems.
I am Manohar Pai, professor from MIT, Manipal. Of course, where Satya Nadella is alumnus as well as he did his BTech from there. I have a question about data model. Because every one of you have highlighted the importance of data model in solving big data analytics problems. In software development, there is a data, model checking and verification. Is there any research going on in verifying whether the model is correct or not? That is model correctness, checking and verification. Is there any such research going on in this area? I just wanted to have comments from you.
Well, I'm not sure if many research works are going on about that. But what I do know is that recently that a lot of people worry about that in the future that the AI is going to maybe change the human world or something. But then the Triple AI Society president they wrote a letter, okay, to tell people no, we don't worry about such things. But in their letter they did highlight once they think, instead of worrying about that one day those robots can conquer the whole world, no, that's not something we should worry. But they did highlight one very important thing in the future AI research is that how to ensure that our machine learning models they are correct. They don't make a silly mistake, so that suddenly that a lot of things just don't work. Yeah. So right now, let's consider something very important. But I don't know if validating machine learning has been if we already have good results on that. Probably not yet. So maybe still a good research direction. Yeah.
Most of the time, model is built on assumptions, and if assumption goes wrong, the model is no good. Only thing is, at least if there is some tool to verify that, okay, whatever the model is developed is to the...
Well, but I guess verification of software is easier than machine learning. Because machine learning models are a bit a bit more dynamic, so it's not that easy. But certainly that's very important.
Actually, there is some work that is going on at Microsoft Research India along that direction. So I'm not sure if anything has been published so far, but Aditya Noori, he's heading a project where he is using programming languages. He's a programming languages guy. So he is using some of those techniques to validate or check a model, whether it is correct or not. But I think at the basic or the heart of it, the approach is based on simple cross-validation, that you have a holdout set. If your algorithm or model works well on the holdout set, then it's good. Then you don't care much about it. But then he has some things more. So maybe check his webpage. I'm not sure if anything has been published so far.
Hi. So my name is Pawan Topo and I'm a PhD scholar from IIT Kharagpur. I just want to clarify about, you talked something about contradictory features. Could you elaborate more on that? I haven't heard that idea before.
I think I just said if you have more features that are correlated with the ones that you have previously, which means that if the previous features, the features with which you are predicting something about your data, some kinds of features are predicting some kind of output that you care about. The new set of features, if they have similar information about what you're trying to predict, then they are positively correlated with your existing features. But it could happen that the previous features just covered a small dimension of your space and couldn't do prediction for the whole thing, and the new set covers the remaining part. So together they may end up giving you a better coverage of the data space. And one crude example of that is also when people train complicated models, they often, to prevent overfitting, they synthesize all sorts of new data points which try to cover the space of features so that the model that you train can actually do accurate prediction for the entire space of potential features rather than just for the small number of features that you input the first time. So I just use correlation not in a very formal sense, but having predictive power which does not contradict what the previous features were trying to predict. Because if you have some features which say this is a cat, but the new features they somehow lead you to a different conclusion, then these are not really suited for the same task.
Yeah, this is regarding deep learning methods because a lot of young researchers are interested in it. Yeah, I'm Satyam, sorry. I'm Satyam from IIT Bombay. I'm a PhD scholar. Okay, this is regarding deep learning methods. So it got mentioned that deep learning methods are black boxes. And it doesn't seem to me like that because the most simplest of neural networks that get used, the feed-forward neural networks, each of the processing units seems to be like a logistic regression unit if the activation function is a sigmoid. And in the early 90s, there was a concept of stack generalization in machine learning, where it was basically an ensembling method, where instead of using some arbitrary method like majority vote to get the final result out of multiple machine learning methods, we trained a different model at the final level from the results of a penultimate level of machine learning methods. So each of the new layers in the neural networks can be seen as a stack generalization, basically, from the logistic regressors of the previous layer. So it doesn't seem that unprincipled to me, a method that it might be called a black box, because the panel didn't seem very happy with deep learning networks.
You're not recording this, right?
So you think that because from one layer to the next layer, we are combining several logistic regression. Okay, so that's a kind of ensemble of models. But turns out that I don't think we already have enough understanding about ensemble of models. So, like, do we have good theoretical support saying that why doing ensemble of different models actually improve, give you better performance than that of a single model? I don't think we are very clear about that. So it's about almost maybe 80 years ago since the Netflix competition. They started using like 100 models or something. But at that time in the beginning I thought, well, why not using 100 models? I mean, that's just totally ridiculous. But turns out that works. Then in the subsequent competitions, ensemble becomes a necessary part in order to win a competition. So now that's another thing, like it works, but we don't know much about the idea behind it. Yeah. That's what I think.
We probably have one question and we'll ask for concluding comments because I think we're running out of time.
Yeah. So, my name is Sonal Singh. I'm a master's. It's okay. I'm a master's student from IIT Kharagpur. My question is specific to Professor Surajit. You talked about optimization and deep learning in your context. So are you kind of working in scaling the networks, optimization setting, or providing theoretical guarantees to the deep networks, or something else?
So I think maybe mathematically we may remain too far from giving theoretical guarantees on the rate or power of learnability that this network may achieve. The easier task that I was talking about is that people are training the parameters of these models, the weights, etc., using some simple methods. Can we understand these optimization methods better for these difficult non-convex problems? One, so that we could maybe speed them up to use converge faster. Second is if we could, while trying to understand some theoretical properties of the algorithms using which we are training a deep model, we may discover what components within the network architecture matter in which particular way, which may even give us some insight into modeling. But it's I don't know if I can fully clearly answer your question beyond that.
Can you shed some light on learning representations other than deep learning networks, as in some other setting? Like, is there any work going on learning representations on this field? So the more general thing I'm aware of is this conference ICLR, which is Conference on Learning Representations, and people, however, present different flavors of neural network based learning. Or previously people used to do single level dictionary learning. That is one way of learning a
recoding the data. But I don't think there is a broad general kind of impetus beyond the ICLR conference, beyond what that conference collects, but I may be wrong.
We should probably wrap up. I think we originally planned to have 2 sections to this panel. I think we'll take a second section for the next Q&A slot.
Sure.
So otherwise we'll probably overrun too much. So any concluding
comments?
Wishing deep learning the best of luck in the future.
Well, I think my conclusion from this is, I guess, pretty much what we started with, that data representation is important, and data itself, that's why, is important. And finding good models automatically will remain a challenge, but we are interested in all of those things. And contrary to what somebody may believe, the panel is not criticizing deep learning, but as persons with scientific interest, whenever you observe something that works, you should be curious enough to ask why. And if you manage to even get 10% of an understanding why, you may discover other phenomena which may help you solve it even better than what's out there. So that's actually the viewpoint I think most of us probably here hold about deep learning.
Yeah, pretty much. I think I agree with that. What I think we can maybe also take from this is that it's important to really work with the data, and the other thing is it's important to look out and look for different maybe mathematical concepts and different techniques that we could apply and bring into the field to make things work better, have more accurate analysis.
So I'll actually conclude with, so through the panel session I felt that the panel raised like sort of 2 big questions which I feel like are worth whole thesis itself. So one thing was what Chizin was pointing out, that we do not understand ensemble methods at all, but we know that they work very well. So for example, these techniques like random forest work amazingly well, but currently we have very little knowledge of why they work. So that will be like one thesis question, that can you take very simple randomized tree models or randomized forest models and show that they will perform better than their parts. That is, like if you have each of these trees which are not very accurate, but somehow when you combine them, they perform much better. I think that's a open question in the area, and it's worth a thesis. And the second thing is what sort of Suvrit was pointing out, that we have this neural networks and deep networks, and we as sorry, I forgot your name, but someone pointed out that the model is reasonably clear, but what is not clear is how to train it. And currently the theoretical work on deep learning has mostly focused on coming up with different models and very different type of algorithms to train those models. Those algorithms are not very practical, or they are not used by practitioners who are using deep networks. So one question would be, if you can take these practical algorithms, like the algorithms that they work, under very specific models and under a lot of data assumptions, that's fine. But if you can show that those exact algorithms work and they achieve some sort of convergence, some sort of global optima, some sort of rate of convergence, some like theoretical notions that we understand well, that also I think will be amazing service to the field, both to more whatever theoretically oriented people, and also to deep learning in general, or to a lot of applications as well. So that's another sort of big open problem I feel which came through this panel discussion. So I guess we should conclude. So thanks a lot for asking amazing questions, and thanks to the panel.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.